Alright, we are live. Welcome everyone. Can you all type something in the chat just to make sure that you can hear alright? Yeah, so today was Codeforces Round 763. Pretty fun round. A little different in style from some of the more recent Codeforces rounds, but I actually enjoyed the round. I think it combines some of the best parts of older Codeforces rounds and newer ones. There were some pretty interesting problems, but also some problems that were maybe a little bit more accessible and intuitive for beginners. In particular, I thought it was nice that problem A was maybe just not another one-line math problem for a change. But yeah, so as usual, we're just going to go through the 5 problems in order, and I will take questions and answer them as I go. Okay. So starting with problem A. So here a robot cleaner is placed on a rectangular floor. They're moving in each second. They move by DR rows and DC columns. Initially they're moving towards in the, let's see, I guess this is the upper right direction. Yeah, looks like this is the upper right. And then they're just going to, and then they'll just reflect off of any walls that they encounter. And the robot will clean a dirty cell if at any point they're in the same row or the same column. And we have to find the number of seconds until the robot, or until the dirty cell will be cleaned. Okay, so this is a rare div2a that isn't just a math problem. Looking at the constraints, n and m are both pretty small. They're only up to 100, and t is up to 10 to the 4th. And so simulation, even if it ends up running in O of t times n time, will be fast enough to pass. And in fact, we can observe that the robot will clean the dirt in O of min of nm operations. And I'll write this down. And the reason this is true is that it takes O of n operations to sweep through all the rows. Because, like, for example, I mean, we can use this GIF they've given us. The robot's just going to go down through all the rows and then back up, and eventually in O of n operations, it'll sweep through all of them. And O of m operations to sweep through all the columns. And so by this point, by the point that we've done either one of these, we'll have definitely hit either the row or the column that the dirt is in. So what we can do is just simulate the robot's movement until the dirt is cleaned, and that's going to run in O of t times min of nm time, and with t up to 10 to the 4th and n and m up to 100 or 10 squared, this evaluates to 10 to the 6th, which is enough to pass pretty easily. So I'll walk through my code. Here I maintain A and B. A, B is the robot's position, C, D is the position of the dirt. And while we can't clean the dirt, I move the robot, and the and then if our current move takes us out of bounds, then I adjust the coordinate or the directions that we're moving in accordingly. Someone asked in the chat whether there's a math solution with casework, and yes, yes, we can also do this with math if we want. I think it's maybe a little bit more annoying. I know having it implemented this way definitely comes in handy when we end up getting to problem D later on. But if you wanted to do this purely with math, what you could do is you could first find the number of turns until the robot reaches the same row as the dirt, and then the number of turns until the robot reaches the same column as the dirt, and then output the minimum of those two. And in order to find this value, there are 2 cases. The first is that the robot might reach the dirt without ever turning around, and the second is that the robot will turn around before it reaches the dirt. And so, yeah, you can split into those cases, and then you can compute these number of turns, and that will get you a correct answer. But alternatively, you can just simulate. Okay, so that's problem A. All right, problem B. So we have a set of disjoint ranges of integers, and initially the set is going to contain just the range 1 to n. And in each turn, we pick a range from S, and Bob picks a number in the range. This number is D, and then LR is basically split into two ranges by removing D and then taking the left part and the right part. And we have to find the number D that was chosen corresponding to each range. So there are a couple of ways we can think about this, but a visualization that I think is maybe helpful to make this problem more intuitive is to try drawing the ranges in sort of a tree structure. And the motivation for doing this is that each range we're going to split off into like a left subrange and a right subrange, which kind of looks a lot, which we can kind of think of as being like a binary tree. And so if we look at the last sample input that they helpfully describe for us here, if we think about the first range as being 1 to 5, then D equals 3 is chosen, and so we can then split it into 1 to 2, and 4 to 5. And from here, we take out 1 from 1 to 2, and then that gives us, we have no range on the left, but then we just get 2, 2 on the right. And we take out 5, and then we take out 5 from 4, 5. And we end up with 4, 4. And then we just take out 2 from here and 4 from here. And this is a helpful visualization, in my opinion, because it maybe helps illustrate what happens when we choose a given D within L to R. And what we can see is that any D is going to appear in all the ranges above it on the tree. And so, for example, 1 here, it appears in this range, it appears in this range, but then it's not going to appear in any of the lower ranges. Like 1 doesn't appear in this range, for example. But meanwhile, any other element in L to R, anything other than D, is also going to appear in all these higher ranges in the tree. So, for example, 2 will appear in this range and this range. But then, moreover, the other elements in L and R, everything but D, will also appear again in the next range down below. And so what that tells us is that all the elements other than D and here I'll write this down actually, everything other than D appears in all the same ranges as D, as well as at least one more range. And therefore, D is whichever element of L through R appears in the fewest of the input sequences. And so from here, we just need to compute the number of elements, from here we can just compute the number of times each element appears in our sequences, and then we can find which one for each interval within that interval appears the least number of times. And there are a couple of ways to implement this. Luckily, n is only up to 1,000, so a pretty simple n-squared implementation will work. It would actually be a pretty standard data structures exercise to optimize a solution to run an O of n log n, which I'll let anyone interested think about. But the way I did this is by maintaining this array CNT that stores the number of times every element appears. I don't really know why I sorted this. The sort is not necessary. And so then I compute the number of times each element appears by iterating over each interval. Then, and so then for all I up to n, I find the element that appears the fewest times in the interval. And so if the current element appears fewer times than the best one, then the current element is now the best. And then I output that best element. Some other people are doing this with maps. That is also feasible. It might add an extra factor of log n though, and so you may want to be careful there. For what's worth, the n log n solution is to, or at least the easiest n log n solution is to use a lazy segment tree. Can this be done with sets more efficiently? I'm seeing a lot of people who are claiming that they have n log n with sets, but Yeah, I guess so you can compute, yeah, so you can compute the number of intervals in which each element appears in O of n using a prefix sum style technique, and then, yeah, and then I guess, yeah, and then you just have to do these range minimum queries. And so you actually can do it all offline. So a lazy segment tree might be overkill even if you're trying to do this in n log n. But anyway, yeah, and AMV Master says, what if we iterated from smallest segment to largest and then find the smallest unused element? That would work. That would work too. And the yes, that would be correct, because for any sequence, any element except the current D will be D in some smaller subsequence. And so if we iterate in increasing order of size, then we can pick. Then there will be only one element in each sequence that hasn't been chosen yet. And so maybe that's what people were talking about when they said they were using sets. Yeah, so that works too. A lot of ways you can do this problem. Okay, so I'll take some questions now. Someone asked, do you recommend the CSES problem set to get better at Codeforces? It kind of depends. I would say it'd be useful if your limiting factor in terms of improving at Codeforces is that you just don't know enough standard algorithms. Like if there are a lot of problems that people just kind of write off as standard that you're not able to solve, then practicing from CSES might be helpful. But I would say that if you're struggling more with sort of ad hoc ideas, or if you know, or if you see a solution and you know the general algorithm that's being used, but you didn't see how to apply it, then I think CSES might not be very helpful for that purpose, because most of the problems on CSES are designed to be pretty standard. Someone says, please do something. There are a lot of cheaters on Codeforces. Not really sure what I'm supposed to do about that. You should take that up with the Codeforces administrators. Yeah, so that's problem B. Someone also asked, is HUOJ good for improving ratings, Project Euler? I'm not particularly familiar with either of those resources. My understanding is that Project Euler maybe focuses on a slightly different breed of math than Codeforces emphasizes, and so it would really only be particularly helpful with a certain subset of the number theory problems that Codeforces has. So, yeah, I mean, I don't know. Honestly, if your main goal is just to improve your Codeforces rating, then you can't really go wrong with practicing Codeforces problems. But honestly, I would just find whichever resource has problems that are most interesting to you and then focus on that. Okay. So, problem C. So we have n heaps of stone, and the ith heap has hi stones, and what we're going to do is we're going to iterate through the heaps from the third to the nth heap in order, and for each heap, we're going to choose a number d, and we're going to move d stones from this heap to the heap 1 to its left, and 2d stones from the current heap to the heap 2 to the left. And so we can... and so some heaps can become empty, but they'll still be counted. We have to maximize the number of stones in the smallest heap at the end of the process. So the overall approach that we're going to employ is that we'll binary search for the answer. And there are a few ways that we can motivate this, a few reasons we might think to do this. The first is that the binary search property is pretty clearly satisfied. So in other words, if we can arrange the stones such that or if we can make our choices of D such that the smallest heap will contain at least like 7 stones, for example, in this first case, then we can definitely arrange the stones such that the smallest heap will contain at least 6 stones, because the same arrangement will work. And so the binary search property holds, so binary searching is valid. But I think even though the binary search is valid, the reason we want to do it here is that there's no particularly obvious greedy strategy here. It's not really obvious what values of D we should choose. And doing a DP solution or something along those lines seems like it's going to be too slow, because the state is going to need to encompass, like, I don't know, maybe if we did the state might involve the specific value of D we chose at the last step, maybe, and there are way too many choices for that. hi can be up to 10 to the 9. And so we can't really do DP. So, but if we binary search, if we know that our goal is just to ensure that the smallest heap contains at least k stones for some k, and I'll write this down. then it turns out that we can employ a pretty nice greedy strategy. We should make we should take as many stones from each pile as possible while leaving that pile with at least k stones in the end. So yeah, so that's a motivation for binary searching the answer. I think also, like, especially with the div2Cs involve binary searching all the time. And so if you ever like are working on a div2C and you don't really know what to do, you should be like thinking through a standard bag of tricks, and it's going to be DP a lot of the time. It's going to be binary search a lot of the time. And so you should be thinking about all those things, and if you're stuck, just try and figure out, okay, you know it's going to be one of this relatively small set of techniques, so let's figure out which one it is and then how we can get it to work. All right. So now let's think about how to solve the decision version of the problem, whether we can whether the smallest heap can be made to contain at least k stones. And the greedy strategy might not be immediately obvious because we might want to leave a heap without k stones on one move, but later add stones from a position to the right to bring us back to k stones. And an example of this is the first sample case. The optimal strategy is to take 9 stones out of pile 1 in order to get to, I believe, what was it? It was 7, 5, 1, 100. And now this third pile, we've dropped it to below 7 stones, which seems bad. But then we can get it back to 7 stones if we take enough stones out of the right pile. And so so that makes it a little hard to immediately determine how many moves we should, or what DI should be for each I, or what D should be for a given I. And so let's think about what information we need to know in order to decide how many moves we should make in a given pile. It turns out that if we already know how many moves we'll make in piles I plus 1 and I plus 2, then we know how many moves we can make in pile I. Because our moves for pile I have to satisfy 2 constraints. First of all, hi minus 3d has to be at least 0 because of this constraint here. We can't move more stones from the pile than that are already in there. And secondly, hi minus di, the number of stones left in pile I, plus di plus 1, the number of stones that we get out of the next pile, plus 2d I plus 2 has to be greater than or equal to k. And what this condition is saying is the number of stones we have after processing all the moves has to be at least k. And so what this tells us is that d of I has to be less than or equal to h of I over 3, and d of I has to be less than or equal to h of I plus di plus 1 plus 2d I plus 2 minus k. And so we can take whichever of these two upper bounds is smaller, and that's going to be the number of moves we're going to make at position I. So, oh yes, this should be a 3di, and so this should also be divided by 3. Yeah, and so let's see. So Sarosh is saying that D can be different for different heaps, correct? Yes, that's right. And that's given in this last constraint here. Okay, so I'll show you my solution. So here, first of all, if any pile we already know that we can't get to k stones, then I just say no, that this configuration is not okay. Otherwise, what I do is I figure out the minimum number of stones we can take away, which is the lesser of either the number of stones we have in excess of k before we perform any operations, or the original number of stones in the pile, because h is storing the original number of stones and a is going to store the final number of stones after the operations. And then I just perform an operation with d equal to rem over 3. And then as long as these last two piles are both have k stones, then we're good to go. Okay. And so as far as far as the binary search implementation, pretty standard. And then I can just print out the result from the binary search. Let's see. So I'll take a look at some questions now. Nala asks, can you repeat what you wrote in line 7? Yeah, so essentially, if we've already decided how many moves we're going to make in piles I plus 1 and I plus 2, then we know that we know the values of di plus 1 and 2di plus 2. And so we know that the number of stones we're going to be left with in pile I is this expression where everything except di is constant now because it's known. We know what hi is, and if we know, and we've chosen di plus 1 and di plus 2 already. And so that lets us compute the exact number of moves we can make so that we don't drop below below k stones in the end. Someone asked, I couldn't solve this a, should I now try to solve 50 div2a so this doesn't happen again? I think looking for setting like a large specific goal for the number of problems of specific types to solve maybe isn't the most productive thing to do, because it may be that you solve a few more similar problems and then you're good to go. I would say if you had a hard time with this div2a, I would try start solving some easy simulation problems until you get to the point where you feel confident with simulation problems. And let me see if they do they have a simulation tag here? I don't think so, but I think maybe what you can do is filter the problems by brute force and then solve like whichever ones are maybe lower than a certain level of rating, and that'll help you start thinking about when you can use brute force techniques and how you can implement them. Let's see. So, some other questions. Sarash says here D is the same as line 12. This should be DI. Here I'm using, this is a slightly different notation from the problem, but I'm using DI is the choice of D made for pile I. Someone asked what extension am I using for Codeforces. First of all, this complete problem set page, it's available at this link on the dashboard, so that isn't an extension. The only Codeforces related browser extension I use is Caret, which is available in the Firefox and Chrome extension browsers, and that I use just to give me rating predictions. And several people are asking whether mid should be equal to L plus R plus 1 over 2 or L plus R over 2. So this is a good question. Basically, if you're setting low to mid and high, or high to mid minus 1, then you use low plus high plus 1. But if the binary search looked like this, if we were setting high to be mid or low to be mid plus 1, then we would use low plus high over 2. And the idea is that, and I think the easiest way to think about this is to think about there are a couple of ways you can think about this. I think just trying out some small cases can help, but I think the easiest way to think about this is to write out like what you're going to do if a certain value is acceptable and if it's not. And so like here, for example, we're saying, okay, if this value is possible, then the answer is at least this thing. And then you want to set your choice of mid so that you're never going to end up out of bounds. And so here we might be decreasing mid by 1, and so we don't want mid to, and so if mid is low plus high over 2, then if low is, and so like let's say that low is 0, high is 1, then if we had mid equals low plus high over 2, then we might set high to be mid minus 1, which is -1, which is outside our range, which is a problem. And so what you can do is you can write out these constraints, and then from there you can think about, okay, if low and high are 1 apart, which of these two choices is going to make sure that we never go out of bounds. So that's how Yeah, so that's how you do this. Plush asks or Fuchsia asks is if there's an iterative way of doing binary search. Yeah, this binary search right here is iterative. There's no recursion going on here. I put OK in this function just because that generally makes it slightly easier to implement. But theoretically, you could put all this code, you could slightly modify this code and then put it in the main function and it would still work. All right. So let's see, what else? Someone asked to explain OK function again. I'll go over it briefly. If you're still having trouble, feel free to rewind the stream and watch the explanation there again. But essentially what I'm doing is I'm going through the piles in decreasing order, and I'm finding the number of stones we can remove from each pile. And this is the minimum of two things. First, we need to make sure that the final number of stones we're going to be left with is at least k. And a of I is like the number of stones in the pile after processing the additions from piles I plus 1 and I plus 2. And so we need to make sure that after adding stones from the next two piles, but then performing our removals, we're left with k. And then secondly, we can't remove more than h of I stones from the current pile because h is... we can't remove more than h of I stones because h is the number of stones we have when we process this pile, and so we can't be left with a negative number of stones. And from there, I just process the move. Several people are asking how I identify that binary search could be used for this problem, or more generally, how to tell whether a problem satisfies the binary search property. So here, I guess first of all, as far as how we know that we can use binary search, the idea here is that if the binary search property is satisfied, because if we can make sure the smallest heap contains at least 7 stones, for example, then we can definitely make sure it contains at least 6 stones. There's never going to be a situation where, like, okay, maybe we can make the smallest heap, or, actually, hold on, how do I want to phrase this? Yeah, basically, if we can make the smallest heap contain at least k stones, then we can make the smallest heap contain at least k prime stones for any k prime less than or equal to k, using the same configuration. And I'll ask, should I iterate from back? Yeah, and you can end. This is a macro that I use, but for D, the D is for decreasing, so the D is increasing from the backwards. But as far as how I thought about binary searching for this particular problem, basically I thought about doing a non-binary search solution. And I realized I don't really know how I would choose D in that case. I couldn't really think of an easy greedy strategy, and the constraints didn't motivate a DP of any sort. So it just seemed like I wasn't going to be getting anywhere, or I wasn't getting anywhere from like solving the general problem. And so I thought, okay, this satisfies the binary search property. Let's see if the decision problem is any easier. And the decision problem is where we're trying to see, okay, can the answer be at least k, rather than saying what is the answer exactly. And so then once I started thinking about the decision version of the problem, I came up with this greedy strategy, and that got me to the solution. Lonely asks, isn't this minimum function always going to give a of I minus k? Not necessarily. And that actually comes up in the first sample test case. In the first test case, we end up if k is 7, for example, then in our first move, we end up taking or performing 31 operations, or we end up taking d equals 31 from the first file, and I'll just show you what that ends up getting us. We end up getting 2 and then 2 plus and then 64, 41 100th, and so then a of I minus k for the third pile is equal to 41 minus 7 is equal to 34. But then h of I is equal to 10. And so it is possible that this constraint where we're not allowed to put the pile into give the pile a negative number of stones in the middle of the process is going to be a binding constraint. Now I'll ask how I computed di plus 1 and di plus 2. The same way I computed di, because I'm just iterating in decreasing order. And so by the time I'm processing pile I, I've already processed I plus 1 and I plus 2, and so I know what di plus 1 and di plus 2 are. Let's see. So someone asked whether it's better to practice by difficulty or by category, or by category like div2b, normally I use the rating or like the rating difficulties to practice rather than practicing like, I don't know, I guess for me it would be like div1ds or div1es or whatever. Yan asks how many, or what's my words per minute. Depends on the day, but I would say like on average maybe between 120 and 130. And someone asks how to type fast like I do. Mostly just a lot of practice. I know my brother is actually a much faster typist than I am. He has a typing YouTube channel that he used to run, and he has made it to 200 words per minute on numerous occasions. So I am actually not the fastest typist in the family. But anyway, yeah, that's problem C. Thanks for all the questions, everyone. It seems like this was kind of a tripping point for a lot of people. Difficult problem. Yan asks, do you type with all your fingers? Yes, I do. Nal asks, what's your age? I am 21. Someone asks, what's the name of my brother's YouTube channel? I will post a link in the chat. Okay. So let's look at problem D. So this is the same problem as A, except that now the robot is broken and it only has a probability of p over 100, which I'm just going to call p, big P, just so that I don't need to write this 100 denominator a bunch of times. And there's a probability p of cleaning each the dirty cell whenever we're in a position in the same row or column. And now we have to find the expected time to clean the dirty cell. Okay. So let's start by thinking about the structure of the robot's path. So notice that the robot's position and its movement directions uniquely determine its next position and direction. So in other words, if we know where the robot is now and we know what direction it's facing, then we can tell where it's going to be in 1 second. And so the robot has O of nm states, where a state consists of the position xy and the direction vector dr dc. Because there are n choices for x, m choices for y, and then 2 choices for dr, 2 choices for dc. And so from here, each state uniquely determines the next state the robot will visit. So we can think about the robot's movement as being modeled by a functional graph. Another term we can use for this is this also happens to be a Markov chain, but I'm going to use functional graph because that generally comes up more in programming contests. So the key property of functional graphs that we're going to use here is that if we start at a vertex and traverse the functional graph, we're going to visit some number of states, possibly 0. And then we're going to end up in a cycle that we're going to repeatedly traverse forever. And so, for example, we might visit states 1, if we just number the states arbitrarily, we might go states 1 to 2 to 3 to 4 to 5 to 6 to 7, and then back to 4. And so here, the path would be 1, 2, 3, and the cycle would be 4, 5, 6, 7, and we would go 4, back to 5, 6 to 7, and so on. And to be clear, I'm just talking about a functional graph in general right now. Obviously, we haven't given all of the states 1 number, so this isn't a specific case for this problem. I'm just showing how we can decompose a traversal of a functional graph into a path and a cycle. And so to start, what we're going to do is we're just going to compute the path and the cycle for the functional graph in this problem. And so we'll simulate the robot's movement again until the robot until the robot reaches a state that it has already visited. Then we can split the the states the robot has visited into a path and a cycle, and we can determine which states could potentially clean the dirty cell. And by the way, I'm seeing a few questions going back to C. I will address those in a moment once I finish this explanation. And so now we need to use this information to find the expected amount of time to clean the dirt. So the first thing we'll do is we'll find the answer if the dirt is cleaned while we're on the path. Okay, so what we're going to do is we're going to maintain a probability that I'm going to call R is going to be the probability that the dirt has not been cleaned yet. And from here, we're going to iterate over the steps on the path, and if at step I we could potentially clean the dirt, i.e. we're in the same row or column, then we're going to add R times P times I to the answer, since there's a probability R that we'll get to step I without already having cleaned the dirt. And then a probability P that we proceed to clean the dirt at step I. And then this, so we add I to the answer with probability RP. And someone's asking, can the cycle length be n times m over 2? Yeah, it might be. I need to think about how large it can be because we also have to factor in the because the robot is only going to visit NM. Actually, no, it might visit all NM positions. So yeah, I'm not sure we can bound the length of the cycle beyond 4 NM. I guess we probably can, but I don't know what the tightest bound is. But we can say that the length of the cycle is going to be at most O of NM. Okay, and so this lets us compute. This lets us compute the answer given that the dirt will be cleaned before we reach the cycle. So now we have to handle the cycle. So what we're going to do is we're going to start by just computing the answer, assuming we start at the first vertex of the cycle. And we're going to employ a pretty similar approach. So let's let RC, just for a cycle, be the probability that the dirt has not been cleaned yet while traversing the cycle. And again, if at step I we could potentially clean the dirt, we're going to add R times P, RC times P times I to the answer. And then R, and I should have set this up here, but R is going to be multiplied by 1 minus P because now there's a 1, because now the chance that we won't have cleaned the dirt yet is multiplied by 1 minus P because there's a P probability that we will clean the dirt. And so similarly, and so here RC is also going to be multiplied by 1 minus P. Now the trick for the cycle is after the size of the cycle steps, we'll be back at the start of the cycle. And so at this point, the answer for the cycle is going to be equal to, let's say that this thing is, we're going to call it value, and value is essentially the contribution of one loop around the cycle. So first of all, if we clean the dirt in the first loop around the cycle, then the contribution from that loop is val. But on the other hand, there's an RC probability that we go around the cycle, which takes size of cycle steps, and then the expected value of the number of steps it's going to take is the same as it was at the start because we're back at the first vertex again. And so we add ant cycle. And so this gives us an equation that we can solve for ant cycle because we know what val is, we computed it here, we know what RC is, we know what the size of cycle is, and so the only unknown variable here is ant cycle, and so that's just a linear equation that we can solve. And so now let's compute the overall answer. So the answer is, and we're going to do this in a similar way. So the answer is going to be equal to the contribution that we got from the path up here, plus there's an R chance where R is what we use, the one we use for the path, so up here. There's an R chance that we end up not cleaning the dirt at any point along the path. We end up getting to the cycle. So it's R times the size of the path, plus, or because that's because we're going to go through size of path steps, plus cycle contribution. Because this cycle answer, I can just say and cycle, since that's what I called it before. Since and cycle is the number of steps we're going to take if we start at the first vertex of the cycle. And so I'll walk through my code, which pretty directly implements this same idea. So the simulation step is exactly the same as it was before. I use a set to store the positions that we visited, and then I have this vals that's going to store the states in the order we visited them. And so from here, as soon as we reach a state that we've seen before, I break. I call that state cur, and then the states, and then in vals, the states that we reach before we hit cur are the path, and the states afterwards are the cycle. So then I iterate through. I first start by computing. I use remprob to represent RC and initval to represent and cycle. And so I start by computing. I use initprob to represent val. Initval, sorry. Initval represents val. Remprob represents RC, and then and psych represents and psych. And so I compute and psych, and so using exactly the same approach that I just discussed. And then I reset remprob. Now I'm going to use it as R, and I'm going to use ans to represent the path contribution. And I compute the path contribution, and I add R times the size of the path plus the cycle answer. And that gets us our result. Okay, so let me go back and take questions. Mayak asks, what difficulty would you give problem C? I don't know. I'm a terrible judge of problem difficulty. 2,000 solves. I mean, I don't know, maybe... Well, here, so let's see. So it's got 2,000 solves. The rating performance of like around 2,400th place is, what is it? Around 1488, so... But it also looks like a lot of people got C without B or whatever, and so... I guess I'm going to guess that maybe C would be around 15 or 1600. We'll see. Ishan asks how to improve at solving div choose C's. I would say a lot of practice. And in particular, I would say rather than focusing on div choose C's in general, I would break them down into more specific topics and think about what exactly you struggle with. Because there are really not that many topics that commonly come up in div choose C's. A lot of them are just ad hoc math problems. A lot of them are like binary search the answer. A lot of them are dynamic programming. There are maybe a few things I'm forgetting. But if you feel like you're having a harder time with one particular area than the others, then I would say then I would recommend focusing on that specific topic and solving a bunch of problems until you feel more confident with it. Let's take a look. Yan asks, why does this work? Because we may stay in the cycle for an infinite amount of time. So we actually, so this is the proof of this is beyond the scope of this problem, but it actually is guaranteed that after some amount, that we actually can show that after some amount of time, we are going to eventually like clean the dirt and leave this and finish the cycle. The idea here is though that, or the reason this equation works for computing the answer for the cycle is that if with probability RC, we end up going through the cycle once and then returning to the initial vertex, then the expected amount of time it'll take after we get back to the initial vertex is the same as the initial answer, because and cycle is the expected time if we start from vertex 1 of the cycle, where vertex 1 is just the first vertex. And yeah, so someone else is asking if the robot can move infinitely without cleaning the dirty cell. So theoretically, like, yes, technically, like, it's possible, but but infinite movement, never cleaning the cell, occurs with probability 0. And that's because like, essentially, if we repeatedly have like a p chance of cleaning the cell, then we're going to have a probability 1 minus p event occurring infinitely many times, which occurs with probability 0. Yeah, so there's no way, or so in general with all these problems, even if theoretically it's possible for the robot to never clean the cell, it occurs with probability 0, and so it's not like there's an infinite answer. And this is something, by the way, I would encourage looking through a good probability textbook, because a lot of this stuff is would be addressed in more detail in a course in probability theory. And that's going to provide maybe a clearer, or maybe a more detailed explanation than I can do. And yes, okay, what happens if we stay in a cycle multiple times? So the idea is, so Ant's cycle is the expected time it's going to take if we start from vertex 1 of the cycle. And so if we go through the cycle more than once, then, so val stores the answer if we, stores the contribution of the case where we find, or where we clean the cell within the first loop. And so essentially, we're computing Ant's cycle is the sum of two cases. So case 1, we finish in the first loop, which is val. And case 2, we don't finish in the first loop. So then, this happens with probability RC, and then size of cyc, which is, and then we have size of cyc, which is the time we spend in the first loop without cleaning the cell. And then we add Ant's cycle, because Ant's cycle is the expected amount of time before we clean the cell. And the reason this is true is Ant's cycle is the expected amount of time if we start from vertex 1 of the cycle, and after we complete one loop, we're back to the first vertex of the cycle. We're back where we started. And so the expected distance is the same, or the expected value of the time it'll take for us to finish is the same as it was initially. So yeah, and if this is a new idea, I would encourage you to try solving some more expected value problems on Codeforces, because this sort of concept comes up in a lot of expected value problems, so it's an important thing to practice. Okay, so I'm going to move on to E real quick. So here we have a binary tree of n nodes. Each node is labeled with a letter, and we're going to perform an in-order traversal of the tree. And we want to make the in-order traversal create the lexicographically minimal string possible. And what we can do is to make that happen is we can duplicate each node's label at most once. So we can replace C or its character with two copies of its character. However, we can only do this when either our vertex is the root or our vertex's parent has also had its label duplicated. And we can perform this operation on at most k nodes. So now we have to find this lexicographically smallest string representation of the tree. Okay, so as usual, when we want to find the lexicographically minimum string satisfying some condition, we'll start by trying to make the first letter as small as possible, and then we'll make the second letter as small as possible, and so on. And the analog here is that we're going to start by deciding whether or not to duplicate the first letter in the resulting string, then we'll decide about the second letter, and so on. And so in the second sample case, for example, the first letter that we reach is D, so we'll decide whether we want to duplicate the D, and then we'll decide whether we want to duplicate the A, and then we'll decide whether we want to duplicate the R, and then the K, and then, the C, the Y, the A, and the N in that order. And so then we need to figure out when we should duplicate a letter. And it turns out that we should try to duplicate a letter whenever it's less than the next distinct letter in the string. And so in the first sample case, our initial string is BAAB, and we shouldn't duplicate the first B because it's larger than A, which is the next letter in the string. But we should duplicate both A's because the next letter in the string that isn't an A is the B, and that's larger than A, and so we should duplicate the A. And the idea is that if our current character is larger than the next one, then we want to get to the next one as quickly as possible, since the next one is smaller. While if our current character is smaller than the next unique one, we want to duplicate it so that we can have as many of this smaller character as possible before we get to the larger one. So that tells us when we want to duplicate a letter, but when are we allowed to duplicate a letter? So the first thing we have to check is we need to be able to duplicate the letter without going over k duplications in total, since we're only allowed to do k duplications at most. And the second constraint is that we can't have already committed to not duplicating some ancestor of the letter. And so an example of this is in the third sample test case. So here we start with the D, but the next letter after D is A, and we don't want, and so since D is greater than A, we don't want to duplicate D. And so then we get to A, and the next letter of R, or after A, is R, which is higher, so we want to duplicate A. But the problem is, if we duplicate A, then we would also have to duplicate its parent D, but we already said we don't want to duplicate D, and that was our first priority. And so since we've already committed to not duplicating D, we're not going to duplicate A because we already said, because duplicating A would force us to duplicate D, which we already don't want to do. So it turns out that these are the only conditions we need. And when I saw the problem, I was kind of worried that there'd be some edge case where this doesn't work. Like maybe you would have a bunch of copies of the same letter in a row, and it would be optimal not to duplicate the first copy, but then to duplicate the second, or something weird like that. But it turns out that these conditions are always optimal. And I'm not going to prove this claim in full detail because it would get pretty caseworky. And I would encourage you to read the editorial if you're curious about formal proofs. But to be confident in my solution, I ended up stress testing it, and when it passed for a few hundred test cases I generated on my own, I sort of felt good about its chances to pass the full test set. So, as far as my implementation, there are a few details to work out here. I end up doing 3 DFSs. The first DFS I use just to compute the in-order traversal of the tree. And so I DFS through the left branch, and then I push V to the order, and then I DFS through the right branch of the tree. And so then I compute the string next, and next is going to store the next difference, the character in the string after the current character. So that's a pretty standard computation. And so then I have my main DFS function, and this is where I decide which characters we're going to duplicate. And so DFS takes the current vertex and then LST dupe, which is essentially the number of characters it's been since the last parent we duplicated. And this is important because last dupe is the number of characters we would have to duplicate in order if we wanted to duplicate this character. And so first I DFS through the next branch of the tree, the left branch, because we prioritize the leftmost vertices. And then if we haven't yet duplicated this vertex, and if we want to duplicate this vertex, if the next letter is greater than the current one, and the number of characters we need to duplicate in order to make this happen, since we need to duplicate all of the ancestors that we haven't yet duplicated, is less than or equal to k, then I'm going to go ahead and duplicate this character. So I'm going to duplicate all this character and its parents for all the ones we need to duplicate until we end up reaching a character that hasn't been duplicated yet. And then I decrease k accordingly. And from there, we've decided whether or not we're going to duplicate the current vertex. And if we've decided not to duplicate the current vertex, then we can't duplicate any of the vertices in the right subtree. And this is like for the same reason why we can't duplicate A here, because we already said we aren't going to duplicate D. And so, if V has already been duplicated, then I'll traverse into the right subtree. Because if V has been duplicated, then we might want to duplicate vertices in its right subtree. And from here, afterwards, I know which ones I'm duplicating. I have this array dupe. And so then I'm just going to build the answer. And again, it's the same recursion. I build the answer for the left subtree, and then I tack on the current character. I do it twice if it's being duplicated, and then I build the answer for the right subtree. So yeah, and then Ishan asks, how much should I practice questions of a particular rating until you're pretty confident in your ability to solve problems at that rating, or until the problems are no longer challenging for you? Yeah, so that's the contest. I think that's all. Let me see if I passed system tests. I did. Very good. Let's see. Yan asks, why does it work to only consider next to V? Because after duplicating, the next letter might change. it actually turns out that the next letter will never change. And the reason is that, so let me see, how do I want to explain this? Okay, so let's say that we have like an A, and then the next is B. And so our string looks like A, B, 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 B. Well, the only two things we can duplicate that might make a difference are we could duplicate one of those A's, but that's not going to change what the next distinct letter is. Or we could duplicate one of those B's, but that's not going to change what the next letter is. If we duplicate, and so there's no way to like add like a C in here or anything like that. There's no way to add a letter that's not already present. And so the next array is fixed. Jacob asks, what do I think of the problem set overall? I thought it was a nice problem set. I enjoyed the problems. A little on the easy side, but I think for a Div 2, it's not the end of the world. Like, I feel like a lot of problem authors really overweight, or really like are more concerned than they need to be about the possibility of like a lot of AKs. Here, I guess maybe it needed to be a little harder with 25 AKs, but on the other hand, I think a lot of these people in the top 25 are just alts. There are relatively few legitimate Div 2 competitors who solved all the problems. And I do think the set was nicely balanced and was interesting and like evidently there were enough problems to be interesting for a lot of people. I guess maybe, if I was trying to make the ideal set, I would maybe have made D slightly easier and E slightly harder, but it also seemed like the authors were aware of that because there was a pretty big jump in the scoring from C to D and then a small jump from D to E. And I also don't think that we can achieve the perfect difficulty balance every time. So, yeah. So, I thought it was a good round. Wonder how many FSTs there were, because that also kind of makes a difference in my perception of the round. No. Yeah. I mean, overall, it seemed like it was pretty good. And then SHK asks, what's the fastest way to improve in competitive programming? Just practice. I can't really be too much more specific than that. Just solve problems that are challenging for you. If you can't solve a problem in practice, then learn from the editorial and think about how you could come up with a solution like that in the future. But yeah, I don't think I can really be too precise there. There's no magic bullet, really. Okay. So, yeah, if there aren't any other questions, then I think that is all I have for today. So thank you all very much for watching. Appreciate the support. Enjoy the rest of your day, and I will see you all next time.